Greetings! Welcome back to my video series on AP Physics C, Electricity and Magnetism, where I'm going to be kickstarting Unit 4 over magnetism. Now, in AP Physics C, the class, magnetism is split into two separate units. You've got magnetism, and then you've got electromagnetism. And in this series, I'm going to combine them both into the same thing, where we'll slowly progress into the more modern electromagnetism. But in this first video, I'm simply going to cover conceptually exactly what magnetism is and what makes it so beautiful. You probably have seen lots of magnets before, probably little permanent magnets like this. You may have even seen this beautiful demonstration. But I'm going to take things from the top and try to explain exactly what makes a permanent magnet operate and how the rules of the universe that we use to conduct and communicate our understanding of magnetism. So without further ado, let's begin. And to start, we're going to talk about these little fields. See, magnetism is a phenomenon usually discovered through rocks like magnetite or lodestone or anything that allows us to create a permanent magnetic field. Now, magnetic materials, you tend to find pretty quickly either attract or repel each other without contact, depending on the orientation. So that interaction without contact implies that it's a field force. And in physics, we should start to be pretty familiar with a lot of these things. Other field forces include things like gravity and electric force. So I'm going to get a little table going here, and we're going to align gravity, electric, and magnetic fields all together. And the reason I'm doing this is because, again, fields tend to operate under pretty consistent rules. How we describe a field is by the quantity that creates and has forces exerted on it by those fields. So with gravity, the thing that creates gravitational fields is mass, and so a gravitational field then will only exert forces on other masses. An electric field, as we learned earlier in the class, is created by charges, like a positive charge and negative charge. If we place a charge in an electric field, it exerts forces on those charges. And so it stands to reason that because magnetism appears to also be a field force, that it's going to follow these rules as well. It's going to be created by some specific quantity, and thus it will also exert forces on that specific quantity. The question is, what exactly creates magnetism? So the quick answer to that is that magnetic fields are created by moving charges. And thus, if a moving charge exists in a magnetic field, it will experience forces due to those magnetic fields. Now, that might seem a little strange to you because, again, most of our experiences with magnets revolve around these little things over here, these permanent magnets. And again, if you've seen this demonstration before of iron filings kind of aligning themselves along a magnetic field, you still don't really see any moving charges. Sure, the little filings are moving originally, but they're not really moving once they've reached their steady state. So what exactly is moving in a permanent magnet? And that's where we're going to start here. Now to start, we need to classify what materials magnets are actually made out of. So generally, it's materials like iron, cobalt, nickel that are ferromagnetic, as we call it. And ferromagnetic just means that they're able to be magnetized by an external field to create permanent magnets, like a bar magnet. Now, ferromagnetic materials themselves are described based on these regions within them called domains. And you can think of magnetic domains as regions that behave like smaller bar magnets. It's just magnets all the way down. So I'm going to use this picture here to kind of describe two different scenarios. The first scenario involves a ferromagnetic material that's unmagnetized. Now, in an unmagnetized material, like just a random piece of iron, the domains are all pointing in different directions. Note that they're associated with vectors. When all of the domains are pointing in different directions like that, it's kind of like when you're looking for a net force, but there's forces just being exerted on something in infinitely different directions. On average, that means that the net force on that object is probably going to be pretty weak. It's not cohesive because all of these things are all trying to do things in different directions and they're inadvertently canceling each other out. And so what needs to happen is you need to get all of these domains on the same page, like over here. And if you do that, then you will successfully magnetize the object, in which case you've aligned the domains in a singular direction. If you do that, then all of the arrows will point in one direction and create one pole, and they will kind of enter through another direction, and that would be the other pole. Now, in order to magnetize an object, you can bring a permanent magnet or an external magnetic field in the vicinity of a ferromagnetic material. So if you bring this magnet in, then all of the domains will align toward the south pole of this magnet right here. So in general, you can magnetize a material by putting an external magnetic field in the presence of a ferromagnetic field. A common way to do this is with paper clips. So if you have a magnet around, you can try it out. Now with domains, we have to go a little bit deeper if we want to find our moving charges. So domains themselves are just regions where the magnetic moments of millions of atoms inside of that region are mostly aligned. And magnetic moment here is where we get our moving charge. So in mechanics, when you have an object rotating around a central axis, later on in the rotation unit, you can describe the rotation of that object as having a certain amount of angular momentum. Angular momentum is a quantity that's perpendicular to the path that the object is rotating around. And so we can estimate the direction of angular momentum by curling our fingers in the direction of the path that an object rotates around. In this case, it would be like this. And if you curl your fingers in that direction with your right hand, then your thumb will point in the direction of the angular momentum. Now, if we do the same thing and we imagine something is going on with an electron orbiting around an atom, well, we have a moving charge, and because that charge is moving, we can assume that that spinning electron is going to be generating some kind of magnetic field. And so magnetic moment is effectively just the angular momentum of an electron orbiting around an atom. Additionally, electrons themselves have their own intrinsic spin, so you can almost think of this like the Earth orbiting around the sun. So if the sun is the nucleus over here, and the Earth is the relatively small and light Earth orbiting around, well, there's already some amount of angular momentum that the Earth has orbiting around the sun itself. And then the Earth, having its own spin, generates its own angular momentum on top of that. Now, if we go back to the fact that this is a nucleus and an electron, the electron spinning around this nucleus creates its own magnetic field due to that motion. And then the electron spinning in place through that orbit generates its own magnetic field on top of that. Those two magnetic fields that are generated are called the orbital magnetic moment and the spin magnetic moment. And those two magnetic fields in tandem create one singular magnetic moment for that particular atom. If, with millions of atoms all doing this simultaneously, those fields all happen to line up with each other, then you have a magnetic domain. And that gives you just one cohesive direction that we can then kind of chunk together with all these others to create our permanent magnet. And so to answer the original question, it's electrons and their spin around a nucleus or around just themselves that creates the magnetic fields that we experience with our permanent magnets. And because it's so hard to see that, this wasn't the most obvious thing for physicists to figure out back in the day. And so the way that we figured this out was through more intuitive moving charges, like currents in circuits. And later on in the unit, a lot of these explanations about magnetic moments will make a heck of a lot more sense as we start to uncover how exactly magnetic fields work with more easily recognizable moving charges. So stay tuned for that, and maybe come back to this video later so you can look at it in a whole new light. But this is kind of jumping the gun a little bit, because for a very long time, magnets were just kind of these magical objects. And like I mentioned earlier, the original magnets described by many ancient civilizations and their recordings was a little piece of magnetite called lodestone. And it's theorized that these pieces of magnetite were originally magnetized by lightning strikes, which already seems pretty arcane and mystical, at least in my opinion. Now, again, lots of ancient civilizations knew about this thing, and they all were aware of its pretty interesting properties. They would note that it magically seems to attract metal objects of certain materials, and then it won't interact with other things. Now, it was ancient Chinese geomancers, yes, that's a real occupation, sounds awesome, that used lodestone to create a pretty important apparatus. See, back then, they used magnetite or lodestone to create these little spoons. And the goal of this was that they would take this spoon made of magnetite, they would place it on a little piece of brass like you see here, and that spoon would magically align itself with the southward direction. Now, the geomancers used this for divination purposes, obviously. I mean, it was magic. But later on, centuries later, as people started to study this a little bit more, alchemists and scholars in China realized that this could be a pretty useful tool if designed correctly. And so through this really fine instrument, they created the world's first magnetic measurement device called the compass. And this device was invaluable back then for naval navigation, especially if you were needing to navigate during the day where you didn't have, let's say, the sun due to cloud cover. The compass really was one of the world's original precision measurement devices. And the reason is because it was aligning with a magnet that didn't really seem to be there. But this device was precise enough that it was able to measure Earth's own magnetic field, which is really small, about 40 microteslas. The magnetic field of Earth happens to be generated by a lot of charged moving particles in the convection currents within the Earth itself. Those moving particles generate magnetic fields because they're moving charges. And the Earth has a magnetic field that protects us from solar radiation and lots of other things pretty much every day. Now, as time went on and the scientific method developed, obviously the whole point of science and physics in general is to create a set of rules that make sense of our universe and the phenomena within it. So, of course, we did the same thing with magnetic fields. And so I'm going to go over some of the conventions or rules regarding magnetic fields. The first and most probably obvious is that, again, a magnet either attracts or repels. So if you take two magnets and orient them in different ways, those magnets will either attract each other or repel each other, depending on how you flip them around. This implies that magnets have two operating conditions, or otherwise, two opposite distinct producers. So if we think of a comical little bar magnet like this thing here with a north and a south, we say that magnets have two poles, they're polarized. Although charges have like a positive and a negative, magnets have a north and a south pole. And so imagining field lines, like here, we say that field lines emerge from the North Pole like a positive charge, and those field lines loop around and they terminate on a South Pole like a negative charge. Now these field lines also have direction, and so just like with electric fields, we describe these as vector fields. With any field line, the vectors involved with those lines always point tangent to the field lines at any point. So wherever an arrow is pointing, you can draw a straight line off of that arrow, and that will indicate the direction of the magnetic field vector at that location. Now, the direction of a magnetic field indicates where a bar magnet would align its north pole to if you were to place it at that location. So for instance, if I were to place a bar magnet to the left of this apparatus right here, the north pole should point to the left. And if you place the magnet there, it will rotate itself so that the north pole points in that direction. If I were to place a magnet up here at the top of this little crest, then the magnet should align itself with the south pointing to the left and the north pointing to the right, and that's what we get. If we were to place it here, the north pole should point up and to the right. If we placed it down here, the north pole should point up and to the left. So just like with electric field lines, the magnetic field lines are just indicating where something is going to experience a magnetic force, or I guess torque in this case. Lastly, it's always good if we're trying to communicate information about these things that we have symbols for them. So the main symbol for a magnetic field is capital B, not exactly sure why. The SI unit for it is teslas, but you will also sometimes see units of Gauss for really small magnetic fields, like the Earth's. Now, so far, it's seeming like magnetic fields and electric fields have a lot of similarities. They both have kind of polar types, unlike mass. They both kind of emanate from one and terminate at the other. They both have lines that look really pretty, but there is one very key, very major difference between electric fields and magnetic fields. And to describe this, I'm going to start by kind of refreshing our memory on how exactly electric fields operate. Now, if we imagine that we have just some static charge held in place somewhere in space, we'd say that that static charge in space can emit electric field lines that go on to infinity. Now, that's what this equation over here, Gauss's law, it describes. That if we were to have some random positive charge located somewhere in space, and we enclose that charge in a closed field called a Gaussian surface, then the net flux, or the collective amount of vectors exiting the surface, will far outweigh the amount of vectors going into the surface, meaning it will have lines that just kind of exit the surface and never come back. They go off to infinity. So what that means is, because these lines go off to infinity, we can say safely that a positive charge in space will do a net amount of work. It'll infinitely exert an outward force on another charge based on the electric potential located somewhere around that charge. So if we imagine a little positive charge Q somewhere out in space, and then we put another tiny charge some distance r away from it, well, in electrostatics, we would describe that location to have some amount of electric potential, which is the amount of energy that would be given to a charge per coulomb that's placed there. Now, when you place two positive charges next to each other, they repel each other. So it's this positive charge, if it's fixed in space, is going to push this tiny charge out to infinity. And as it flies off to infinity, the electric potential describes how much energy will be given to it by the time the force is negligible enough that it stops accelerating. And so we would say that the work done on this tiny charge that's flown off to infinity is the quantity of charge that it has times the electric potential, which again is how much energy will be given to it per coulomb of charge that it has. In other words, Q times V is the net amount of work that will be done. So here we see that if we have a charged object, it can do a net amount of work. And obviously it would take a similar amount of work to push this charge back in. But the fact that it can infinitely accelerate an object out to infinity is a pretty powerful tool. Now here's the kicker and the main difference with magnetic fields. They can't do work, period. There's no way, according to physics, at least that we know of so far, where magnetic fields would be able to do the same procedure. So if we imagine that we took one of those bar magnets from one of the previous slides and snapped it in half and just had a north pole and without any south pole, well, we would imagine that it would behave kind of similarly to a positive charge, meaning that that north pole would have magnetic field lines that would all just kind of radiate outwards to infinity. The problem is that simply does not happen. Magnetic field lines from a permanent magnet will always terminate themselves, period. And field lines in general will just never go off to infinity. They'll do anything but that. They will loop around in circles. They will loop around to the other end of the object. They'll do lots of things, but the one thing they will never, ever, ever do is fly off to infinity. They will never do that. And so the main statement to remember is that there can never be any magnetic monopoles. And that's what this equation right here is saying. Note that this equation is very similar to Gauss's law for electric fields, except that on the right side of the equation, there is simply no way that you can have this net flux equal anything other than zero. So the net flux due to a magnetic field around a closed surface is always zero. And that brings us to one of the first major implications about monopoles. So with those two equations, we note that we now have a Gauss's law for both electric fields and magnetic fields. And they both make statements, and conveniently, they both appear on your AP formula sheet this year, which is pretty cool. So to review Gauss's law for electric fields, we've got this nice, beautiful equation right here. And recall that this statement basically says that the net flux, or the net amount of field lines exiting a surface through a closed 3D surface, is proportional to the charge enclosed. So if you have a positive charge, you will have a positive net flux. If you have a negative charge inside, then you will have a negative net flux. If you have equal amounts of positive and negative charge, then your net flux will be zero. All the lines exiting will re-enter the surface later. Now, if we go to Gauss's law for magnetic fields, again, the left side looks pretty familiar. The only difference is we replace electric field with magnetic. But on the right side, it all equals zero. And so again, if we recall that the left side of this is referring to the net flux exiting a surface, we would say that the net flux is zero. So Gauss's law for magnetic fields states that the net magnetic flux through a closed 3D surface is zero. No exceptions, none. Don't even think about it. There is no way that you can have a net flux exiting a 3D surface due to magnetic fields. And so there is kind of an unfortunate consequence of this, which is that Gauss's law for magnetism kind of means that any of those little free energy devices that you sometimes come across on YouTube channels just don't work. They're total bunk. There is no way that any of those machines will work if they're powering it with permanent magnets only. Now, there are ways to circumvent that, and that's how they're able to pull those machines off. But unfortunately, it still means that you have to power it through some external energy source. The main thing here is that magnetic fields will never supply energy on their own. It always has to be manipulated through other means. And that's how usually those machines on YouTube are made. Now, the other implication with magnetic monopoles has to do with breaking magnets. If we can't really have just the North Pole, that implies that if we were to take a bar magnet and snap it in half, we wouldn't have just a North Pole and a South Pole. They would actually turn into two separate bar magnets, both with their own North and South Pole. You can try this if you have a magnet that you're willing to break. I personally don't want to break any of mine. Now, this might strike you as kind of odd, but it makes perfect sense if we go back to our original explanation of how permanent magnets work with domains. If we imagine a bar magnet like this, where its north pole points to the right, then if we go with our original domain understanding, well, that would imply that all of the domains within that material are pointing to the right in that instance. So it would look something like this. If we were to take a bar magnet and kind of overlay it on top, it would basically imply that all of the arrowheads are pointing to the right, which is where the north pole would point, and all of the tails point to the left, and that's where the south pole should be. Now, if we were to take this material and break it in half, well, the thing is, nothing about it would really change between those two materials. With an object like this, well, if we break it in half, none of those domains are really going to have any reason to change. So when we break this object into two magnets, well, the left object is still certainly going to have a bunch of tails pointing to the left and arrowheads pointing to the right. And in the other object, we'll have the same thing. We'll have a bunch of tails pointing to the left and a bunch of arrowheads pointing to the right. In both of these objects, all of the domains are still pointing to the right. They're virtually the same as the original object. And so overlaying two magnets on top of this, we're still going to have two bar magnets with a south pole and a north pole. We cannot have an object with just arrowheads. An arrow always has to have a tail. So a magnet will always replicate itself, even down to the smallest speck. So that's about it for this video. I've introduced Gauss's law for magnetism and hopefully given you a better appreciation for how exactly magnets work. In the next video, we're going to start investigating how exactly magnetic forces operate, and through that, we'll slowly uncover the beauty of magnetism and all of its little invisible fieldy quirks. So until then, thank you very much for watching, and I hope you have a good one. Farewell.